So I'm going to do this. I'm going to look at this problem through a graph set, right? So what I'm going to do is I'm going to take two perpendicular lines as usual, frame of reference. This is so let's look at this graphically. We're going to use Cartesian graph. So let me fix two perpendicular lines. This is my t-axis, this is my s-axis, and then at time t1, so this is s at time t1, time t2, at time t3, T4, T5, T6, T7, T8. So I just plotted the points, right? So S at T1 is this distance, S at T2, S at T3, and so on. I'm just going to join these by some continuous curve. Say, suppose I ask a question like, say I left my house at 1:30 and then reached here by say 2 o'clock, and then the distance is 10 kilometers, and what is my average speed? And you will say I covered in half an hour 10 kilometers, so it is average speed is 20 kilometers an hour. Yes. Right. But then if you are traveling in your two-wheeler or car, and then if you look at the speedometer, say we don't travel at the same speed of average speed 20 kilometers an hour right from, we start from rest. So initially when we start, the speed is 0. Then the speed increases, that is we accelerate, and then at the signal we stop again, right? Again we start accelerate, so many stops, etc. Finally we have arrived at a distance, say traveled a distance of 10 kilometers in half an hour. And the average speed, what do? We look at the total distance traveled and the time interval, divide S over T, that gives you the average speed. So if I ask the question, what is the average speed or I'm going to use, instead of speed, velocity. That's because I'm going to give importance to the direction. Average velocity in the time interval T1 to T2. What is that? See, at T1 the distance traveled is this much, at T2 this. So in the interval T1 to T2, what is the distance traveled? This is the distance, or this distance, isn't it? If it goes along the curve, this is the distance traveled. And then so I can look at the average velocity. Average velocity is, see, I'm moving on a straight line, isn't it? So I look at ST2 minus ST1. Is that right? This is my average speed, average velocity. Now, why did I change speed to velocity? You see that, say, t keeps increasing, but then when if you look at, say, this is T3, it's here, T4 it has come down, no? Yes, it's come down. That means At T4 it's somewhere here, at T3 somewhere, T4 it's returning on the opposite direction.
Yes, sir.
So we see, we look at the two, S increasing and S decreasing. S increasing and S decreasing. Right? So if you take that sign also into account, then speed becomes velocity. So later on we are going to use introduce the word vectors. Right? And speed is a scalar, it doesn't have any direction. And then vector velocity is a vector. So we are giving importance to the directions S increasing and S decreasing. Okay. Good. This is my average speed in this interval. So I can ask the question again, what is the average speed in the interval T5 to T6, etc. Alright. But then you will see that, and if I look at, right. Again, is it always positive?
Time is always positive.
Average T2 minus T1 is positive. The ST2 minus ST1. For example, if I do it in T3 and T4, right? ST3 is this. ST4 is smaller, isn't it?
Yeah.
Right. So if I do it ST4 minus ST3 will be negative.
Yeah.
Right? Be negative. And suppose at say for example at T9 or something it is the same. Then what is the average velocity with T1 and T9? It comes back to the same position.
Yeah.
So it might have traveled so many, but the average speed is average velocity is zero. Zero. So the average speed can be positive, can be negative, can also be equal to zero. It can take any value. Right? Good. So this is what it now. But I asked a question. I was saying about the speedometer in your car or your two-wheeler. It keeps changing, isn't it?
Yeah.
We don't come at the same average speed. The speed changes. Right? The velocity changes. And when the velocity changes, the rate of change of the displacement, that we call the velocity. The rate at which the rate of change of velocity, we call it acceleration. Right? So we at the signals we stop, and then again we accelerate, and so on. Okay. Now, at any instant, it shows at a particular instant, it shows 45 kilometers an hour. Then how does the speedometer calculate that? What does it do? See, actually what it does is, at that instant, it takes a small interval time around that distance, and at that instant. Suppose you are looking at the speedometer at 1 hour, 43 minutes, 20 seconds or something. At that instant, and it takes a small interval of time around that, and then calculates the distance traveled, and then it calculates the average speed in that small interval of time. Right? So if it takes a small interval of time, so usually in mathematics we use the notation delta t for something small. Right? This is a small interval of time. In that small interval of time, the distance traveled is, say, delta s. Of course, if it travels in the s increasing direction, it will be positive, otherwise it will be negative. Right? Now you look at this ratio. Right? This is the average speed in that small interval of time, delta t. But then that is not the instantaneous speed, isn't it? Not at the
Yeah.
Because see, this delta t is a small interval of time. Small is a very relative term. What is small to me may not be small to somebody else. For example, when I was at school, say we used to have a record of all our things maintained in a book, and after the completion of SSLC, we were given a book called SSLC book. There, every month, height and weight, and then your test mark score from your last 3 years, 4th form, 5th form, and 6th form. They were called 4th form, 5th form, and 6th form. And then there was also how much time you took to run 100 meters. That was also recorded. When you were in the 4th form, what is the time you took? When you were 5th form, how much? So, and then how they used to measure this, the physical director will stand in that the other end, and then he'll have a kerchief in his hand, and then he'll wave.
Wow.
Right? And then you look at that kerchief, and then you start immediately after waving. And then he will have a stopwatch, which can measure 1 second. Right?
Yeah.
So, and then, so he measures and say 20 seconds, 80 seconds, 18 seconds for 100 meters. But that's very, very crude, isn't it?
Yeah.
Now you look at your Olympic Games, and then in the swimming pool and other thing, they measure up to 0.00003 of a second, 1 of a second, right? So, the technology has improved, and then it depends on, so what is small? There, even 1 second was considered to be a small time, and then but now it is no longer a small time, then it can measure even 0.00001 of a second, right?
Yeah.
And therefore, this delta t small is a very relative term, right? So, if you want exact, see, you get a better approximation to your instantaneous speed if you look at delta, you take delta t to be smaller. You take still better if you take delta t still smaller. And the obvious question is, no, I don't want any error of, say, absolutely no error. I want the exact answer. That means I should take delta t almost 0. So we look at this ratio and then approach, say, look at what happens to the ratio as delta t approaches 0. Alright? That we call limit of this as delta t tending to 0 and approaching 0. So we look at limit delta t approaching 0 of this ratio. Right? Now, but then your elementary class arithmetic should have taught you that I can divide by any number other than 0. I cannot divide by 0. Division by 0 is not permitted because 1 over 0 doesn't exist. It is not a number. The 0 doesn't have a multiplicative inverse. If you take anything non-zero, say alpha, then I can speak of 1 over alpha, that's so that the product is 1. So every number non-zero has a multiplicative inverse, but 0 doesn't have a multiplicative inverse, and so we cannot divide by 0. But I can take delta to be very small. As long as it is not equal to 0, I can divide. Right? So keep delta t smaller, smaller, smaller. Every time you look at the ratio, and if the ratio stays around something as delta t tends to 0, that we call the limit. And students say who have done some calculus, this we call the derivative of s with respect to t, and then we write it as ds by dt. Right? So that is what the instantaneous speed or instantaneous velocity means. Right? So the instantaneous velocity is this, the ratio, the limit of this ratio. Okay. Let me imagine a particle moving on a straight line with, and also let's look at the this part of it. Say this is the curve. Okay. So this is say t3 minus t2, and this is that st3 minus t2. Right. Now I'm going to see it has taken a curve, isn't it?
Yeah.
But then if my T3 and T2 are very close to each other, right? T3 is very close to T2. That means this interval is very small. Say. Then, although it is a curve, whenever I take a continuous curve, right? If these 2 points are very close to each other, right? Then the curve is almost like a straight line, isn't it?
Yeah.
Right? It's a good approximation is a straight line. Right? So let me join it by a straight line. Then I get a triangle. Right? I get a triangle and I look at this alpha, angle alpha. Right? Okay. Then what is your average velocity here? This by this, isn't it? In terms of trigonometry function, it is tan alpha.
Yeah.
Tan alpha. Right? This is tan alpha. Good. Now, when it tends to 0, see what happens when you are, say, this card, when it B approaches A, right? The card becomes a tangent, isn't it?
Yeah. The point becomes
B approaches A, the card AB becomes the tangent at A. right? So I'll have the tangent. And then that is your instantaneous velocity. And because you look at the, see what happens in the limit, the card becomes a tangent. So if the tangent makes an angle alpha, then tan alpha becomes your instantaneous velocity, right? And that's what you mean by saying that. Say that is the slope of the tangent is your dy by dx, ds by dt. Right? So that gives you the rate, the instantaneous velocity. Now let's look at the velocity keeps changing, isn't it? The distance increases, decreases, this and that, it keeps changing. Now, when is your ds by dt becomes 0? This ds by dt can be negative, positive, or 0. That's what we saw here. Right? See, look at this graph, and when does it become 0? That is ds by dt is just now we saw that the slope of the tangent, isn't it? In slope. Right. So at these points, what happens to the tangent? The tangent is just parallel to the axis, isn't it? Is that right? Yeah. At these points, the tangent is parallel to the axis. So what is the angle alpha that it makes to the x-axis? 0. And what is tan 0? 0. And therefore, the velocity becomes 0 at these points, right? Peaks. At the peaks either maximum or minimum, right? And of course, I am assuming that the curve, the trajectory is a continuous curve. Yes. Everything is based on that, right? So we assume that the particle is moving continuously, that it doesn't jump, right? It doesn't jump. Right? It moves continuously on a straight line. Now look at this velocity. The velocity here, and look at the tan alpha function. No? See, here the alpha keeps increasing, isn't it? The tan alpha is, see, alpha is positive, then it is, so the average velocity here in this interval is positive. But when you look at this, when the curve is falling down, right, decreasing, then this is your straight line segment joining these two, isn't it? What is the angle it makes? It makes obtuse angle. So tan becomes negative, right? It becomes negative. That's what you meant by this can become negative. Now, so you see that the positive, negative, or 0 depends on alpha in some sense. So alpha 0, then it is the velocity becomes 0. So the velocity doesn't remain the same throughout. That we observe. Is that right? So there is a change in velocity. Just as we see that there is a change in the distance travelled as time changes, we observe there is a change in the velocity as time changes. Now, so I can speak of again the rate of change of velocity, right? That is, what is the average change in velocity? Average change in velocity means I had to look at v at t2 minus v at t1. So again the same thing, no? Velocity at t2 minus velocity at t1 by t2 minus t1. That will give you the average velocity in the interval t1 t2. But then if I want the instantaneous, then I can do the same thing. No? I can look at the in delta t, what is the change in delta v by delta t. Look at the limit as this, as delta t tends to 0, and that we will call dv by dt and call it a acceleration. And again, although delta t remains positive, your numerator can take 0 value, positive value, negative value, and therefore this limit can be either 0, positive, or negative. So you can have a positive acceleration or a negative acceleration, or the acceleration can be 0 at some point. Okay. So today what have we learned? See, we learned what is motion. That is, what do you mean by a particle is in motion? It means fixing a reference point, and if I call the directed line segment OP as its position vector, then as time changes, this position vector changes. If the position vector remains the same for all time t, then we say the particle P is at rest. So P is moving means the rate the position vector RT changes. And one observation you have to say, I would like you to make is that, have I marked the origin anywhere here?
No.
Zero. I have not there. And I have carried on the discussion. See, nowhere have I really used its position. That's because I'm just looking at the intervals there. So it doesn't matter where that zero is, right? But to fix things, you see, maybe I require this as some origin. Then I'll have, then you should look at what is the velocity at the origin, that is said t equal to 0, that is the initial velocity and so on. But to speak of the instantaneous velocity or the average velocity and thing, we require only the intervals, isn't it?
Yeah.
So it doesn't matter where that origin is, right? And also, one more thing you should observe is that when you do things on a graph sheet, right? We look at some scales, isn't it? This is some scale, this is some scale. Okay. But then, if I can do it on a big board with, say, suppose my class consists of about 200-300 students, right? Then I cannot use such a small board. I require a big board and I should write in big letters, right? And I may take a graph in which, say, the scale is 1 unit is this much, right? Or if we two people are sitting on a table and then doing it on a small A4 size paper, I may use a smaller graph. Or if you are sitting or traveling in a bus and then I am telling you or say explaining it on the back of a ticket, right? Then I am going to use a graph sheet or graph on a small rectangular sheet, rectangular paper. So my scale will be, see, physics will remain the same. I can say so it is independent of the scaling. Where I take the origin, right? And so these are things you have to note. And actually, in say when you do vectors in more detail, we will learn things which are translation invariant, etc. Right? So next time we will continue with. See, we will take the first a simple problem of a particle moving on a straight line with a constant acceleration. That is, velocity changes, but the rate of change of velocity is a constant with the same acceleration it goes to. Alright? Then, how do I find the distance? We will get some nice equations. Right? And in fact, even before calculus came, people could arrive at these equations. Right? But now we have a nice tool in mathematics, calculus. So we will use calculus and then derive the equations of motion. They are called equations of motion, or a particle moving on a straight line with constant acceleration. You see that in kinematics we use the geometry as much as possible, because this geometry comes to a rescue in explaining many things. And whenever you do something on a straight line, we also try to imitate and try to do what happens when the motion is on a circle, right? So let's look at those things in the next subsequent classes, and then we'll spend some time on deriving the equations, and then we will learn more about the theory by solving some interesting problems.
Thank you.